Alright, so the last video showed where the double angle identities come from in terms of another set of identities, so then this video has got to be how to use them. So we're going to work through an example of where we need to use each of those double angle identities, one for sine of twice an angle, one for cosine of twice an angle. Pretty much if you can find sine of twice an angle or cosine of twice an angle, you can find it for any other of the four trig functions. So, just to refresh from the last video, we went through and showed that cosine of 2 theta can be written in these three ways. Sine of 2 theta, we just had one form of writing it. And then we brought some attention to tangent of 2 theta. This video is not going to work through an example, but we did mention in the last video that tangent of 2 theta can also just be found by taking whatever you found for sine of 2 theta and dividing it by cosine of 2 theta, because that's the quotient identity for tangent. So let's go ahead and give this a shot. The example that I have ready for us involves some given information, and then using that given information along with the double angle identity to answer some questions. So here's what we got. We are going to be given that sine of theta is equal to 2/5, so that's the ratio of opposite over hypotenuse, and we're also given that cosine of an angle is less than 0. Using those two bits of information, we'll start by finding cosine of 2 theta, and then on the next slide we'll find sine of 2 theta. But right off the bat, we can just think about these given bits of information and determine what quadrant the original angle falls in. That can actually be really helpful to know if you've done good work with your final answer. So if you don't mind, think for just a moment about the quadrant in which the sine value would be positive, because 2/5 is positive, and also think about the quadrant where cosine would be negative, because this other given information says cosine is less than 0. So again, we're not actually doing the problem yet, but just some forethought. So thinking about our different quadrants, we know in quadrant 1, both the x and the y are positive. In quadrant 2, the x value is negative, the y value is positive. Quadrant 3, both are negative. In quadrant 4, we're back to x being positive and y being negative. So if in this problem we know that the sine value is positive and sine is the y coordinate, and we also know that cosine is negative and cosine's the x coordinate, that tells me my original angle must be sitting right here in quadrant 2. So again, it's just helpful to think about that. I'll tie back in our answer at the end to the fact that our original angle was in quadrant 2. But probably for now we're most interested in just finding what the question's asking for. So we'll go ahead and get back to that. Alright, so find cosine of 2 theta. That's our goal. Over here on the right, in this box, I've placed the three different forms that we know for cosine of 2 theta. And when we first found those three forms earlier, it may not have been clear why we need three different forms. One should seem like enough, right? But we always want to pick the form that utilizes the given information. So, for example, this first form in this box here involves knowing both cosine and sine. And at least with what I'm given, my only given was the sine value. So I don't think I'd like to use that first form. The second form only involves cosine, which again is not what we were given. But the third form involves sine, and that's what we were told. So I'm going to be using this third form as we work out this problem. So when it says find cosine of 2 theta, I'll jot down the form of the identity that seems most appealing to us, which is 1 minus 2 sine squared of theta. Just a little reminder that sine squared of theta literally means the sine value squared. And sometimes writing it in that form will help us move through this process a little easier. So if this, what I just wrote, is the identity that's true all the time, let's begin applying our values. So we're trying to find cosine of 2 theta, where for us, we know the given sine value was 2/5. So when I hit sine of theta in this formula, I simply replace sine of theta with 2/5. So sine of theta and 2/5 are interchangeable in this problem. Now what remains, of course, looks like some order of operations, so we'll move through that carefully. Using order of operations would tell me to take care of the exponent first. So for a moment, I'm going to keep the 1 minus 2 times. And then when we take 2/5 and we square it, that literally means 2/5 times 2/5. So 2/5 squared should be giving us back, let's see, 2 times 2 would be 4. 5 times 5 would be 25. So that should be giving us back 4/25. So again, just following order operations. Next, we'll go ahead and take 2 times 4/25. And 2 can be thought of as 2 over 1. So when we take 2 over 1 and we times it by 4 over 25, we'll multiply across the numerators to get 8, across the denominators to get 25. And that tells me I've got 1 minus 8/25. At this step, of course, if you're using a calculator, you can get a decimal for your answer. I'm just going to go ahead and keep working it by hand. And to do so, I'm going to think about 1 strategically as 25 over 25. I think you would all agree that is equivalent to 1. And the reason for writing 1 in that way is because of the denominator of the second fraction. So when we write 1 as 25/25, it just makes it more straightforward, more simple for subtracting the 8/25. And I'll just real quick catch up with carrying down the cosine of 2 theta. So we're taking our time with simplifying. So at this point, it looks like we can just subtract those two fractions and end with cosine of 2 theta, is equal to, let's see, 25 minus 8 should be 17 over 25. And that would represent the cosine of 2 theta value for this example. Alright, so what I'm going to do next might not be super clear, but bear with me if you can. Even though we've finished the problem and we've answered it, I want to think about how good of an answer this is. So I'm going to refer back to this little coordinate plane we talked about earlier. When we started off the problem, we were able to determine, based off the given information, that the original angle, just theta, was in quadrant 2. And maybe I'll use degrees to make this a little easier, but that means the original angle was somewhere between 90 degrees and 180 degrees. So imagine doubling an angle that was somewhere between 90 and 180 degrees. And what would the range on the new angle be? Well, let's see, if we double 90, that would be 180. And if we double 180, we'd get back 360. So what I'm doing here just kind of shows me that the resulting angle should be somewhere in quadrants 3 or 4. So it's kind of a broad span, right? Quadrants 3 or 4. But the fact that we just got an answer for cosine of 2 theta of 17/25, that's a positive value. So that's just telling me that my doubling the angle took me all the way into quadrant 4 because the x-coordinate is positive in quadrant 4. So I know that last little bit there may not have made perfect sense, so feel free to stop and discuss. But just thinking a little bit about how we know that our answer is good. So maybe now I'll go ahead and move into finding sine of 2 theta, but again, feel free to stop and kind of dissect that a bit more as you'd like. So the next part of this process, as you might imagine, is finding sine of 2 theta. So in the last problem, we found cosine of 2 theta. Now we're going to find sine of 2 theta. And there's only one form of the identity for sine of 2 theta, so we're pretty much stuck with this form. We still have the same given information, which was that sine of theta is equal to 2/5, and that the cosine value is less than 0. And it's actually good that we talked a little bit about that earlier, because as you notice the sine of 2 theta identity, it involves not only the sine that we were given, but also cosine. So it means we need to do a little bit of groundwork for this identity to work. And again, I think we'll be able to handle it no problem. But let's just start by writing down the basic identity, which states that sine of twice an angle is equal to 2 times sine of the angle times cosine of the angle To share with you where we are in the process right now, applying our values, I'm able to fill in the sine of theta because that was given as 2/5. That was the given ratio for sine. But where I'm feeling a little bit stuck is my cosine value. That's a fraction that we still need to determine. You might already know that the denominator is 5 because the sine ratio is opposite over hypotenuse and the cosine ratio is adjacent over hypotenuse. So they share that same hypotenuse. But what we need to figure out is what is the adjacent side. If we refer back to our coordinate plane drawing from earlier, we had agreed that the angle, the original angle, must fall somewhere in quadrant 2. So referring to that bit of information, as we work on sine of 2 theta, I'm going to draw a little coordinate plane on the side and get a triangle drawn in that quadrant 2. So I'm going to try to interpret the given information with you all. So far, we know that given this right triangle in quadrant 2, the sine ratio for theta is equal to 2 over 5, which tells me that the side opposite from theta, which is this side here, measures 2 units, and the hypotenuse, which is always across from the 90-degree angle, measures 5 units. I believe we can find this third side by applying the Pythagorean theorem. So I'll just write it as x squared plus y squared equals r squared. The x value is what I'm searching for, so I'll keep that as the unknown variable. The y value is the vertical side length, which is known to be 2. And the r value is the hypotenuse, which we were given or understood it to be 5. So we'll just do a little bit of solving here. Looks like we have x squared plus 4 equaling 25. Subtracting 4 from both sides, we get back x squared equals 21. And square rooting both sides, we'll get back technically x equals plus or minus the square root of 21. So just algebraically, we square root both sides, we get back plus or minus the square root of 21. However, the context should help us know whether we take the positive square root or the negative. Since we're in quadrant 2, is the x-coordinate positive or negative? So yep, it's negative, so we're going to put the negative square root of 21 as the label for that missing side. So notice we did have to do a little bit of groundwork to be able to plug into the identity. Our work right now just allowed us to, when we see cosine, correctly find that cosine ratio. So we had already prepared with the denominator of 5 for cosine, and I think you would still agree with that as the hypotenuse. But in place of the adjacent side, I'm going to put the negative square root of 21. So it looks like we just have a little bit of multiplying to clean this up, and we'll go ahead and do that now. So if we go ahead and maybe for the sake of working this out, I'll write 2 as 2 over 1. I'll leave my 2/5, that should be fine. And I'll leave my negative square root of 21 over 5. So since we're multiplying fractions, we can just multiply straight across the numerators and straight across the denominators. I don't see any cross cancellation. So when we multiply in the numerators, 2 times 2 times the negative square root of 21 could be expressed as negative 4 times the square root of 21. In the denominators, 1 times 5 sounds like 25. And that doesn't reduce, so that would be a great way to leave our exact answer for sine of 2 theta. So what really matters in this process, again, is coming up with the exact fraction, like what we just found right here for sine of 2 theta, and what we found a few moments ago for the cosine of 2 theta. But just like we thought about earlier, I'd love to discuss how do we know that this answer for sine of 2 theta is good? Because it could be easy to make a small error in the process. You want to have some way of knowing you've done good work. And maybe I'll appeal to the same process we did when we thought about our cosine of 2 theta. We had talked back with this problem that our answer made sense because doubling an angle in quadrant 2 would produce an angle in quadrant 3 or 4. Because our cosine value was positive, we were able to determine that the angle doubled would land in quadrant 4. In quadrant 4, the x-coordinate, or the cosine value, is positive, and that's exactly what happened for us. By the same token, the sine value, which is the y-coordinate, should be negative. So that means the answer we just got on the next slide better be negative. So let's just go back and check that much. Yes, so it looks like the answer we found was in fact negative, and that does make sense in the context. And I'm debating whether I should kind of talk through an additional check. I'm going to go ahead and do it. So again, if you feel kind of maxed out, feel free to take a little mental breather. But if you're interested in knowing that your work is really, really good, let's think through this a little bit. This is just for fun. So I went ahead and just did this in Desmos because at least we all can access Desmos. So what I did is I actually took the original given information, which said that sine of theta is equal to 2/5, and I just took the inverse sine of both sides to find the actual value of theta. We've started learning a little bit about the inverse functions. So the thing is, when I did the inverse function, it gave me this answer of about 23.58 degrees. I did put this in degree mode to make it a little easier to talk through. Now, we understood, feel free to refer back, but we understood the original angle had to fall in quadrant 2, and that was because we were told at the beginning that cosine of theta was less than 0. So we knew we had to be somewhere in quadrant 2. So this next calculation shows me backing off from 180 by about 23.58 degrees, and that produces a quadrant 2 angle of about 156.42. So 156.42 degrees is the actual original value of theta. Okay, so again, these are all just approximations, but it's going to feel fairly satisfying because what I went ahead and did with that then is I took that angle, which is the original angle theta, and doubled it, right? Because we're working on twice the angle in this problem. When we double it, we get 312.84 degrees, roughly. So again, these are approximations. And what I went ahead and did with that is 312.84 degrees. First of all, we should feel satisfied from our work earlier that this is definitely a quadrant 4 angle. So even though in the process we just worked through, we didn't need to know the angle, 312 degrees is the double angle, is twice the original angle. So then I just took cosine of that double angle, and that gave me roughly 0.68. And then I input the fraction that we had found in our work, just to show you real quick, hold on. We had found cosine of 2 theta to be 17/25. So I just took this answer, typed in 17/25 to find its decimal approximation, and felt really satisfying seeing really that these are basically equal. Due to some rounding, there's a little error, but those are equivalent values for our purposes. In the same way, when I took sine of that double angle, I got about negative 0.73, roughly. And then I went ahead and typed in the value we found a few minutes ago, which was negative 4 square root 21 over 25, and found that decimal to also be about negative 0.73. So again, for our purposes, these values are equivalent. If that check is confusing, don't stress too much about it, but feel free to maybe try taking some more time later to think through it. It's just kind of neat to leave a problem knowing that you've done very good work. So at the end of this problem, we again care primarily about the exact fractions for cosine of 2 theta, which was positive 17/25, and the exact fraction value for sine of 2 theta, which was negative 4 rad 21 over 25. And there are a variety of ways we can check our work with this process.